AC circuits. Chapter 33. Big difference between AC and DC. DC, the charge is always flowing in the same direction. AC, they, yes, plus the A there.
I didn't hear that.
Alternate.
So they're going back and forth.
Yeah.
They tell about the friend whose dad was an electrical engineer, his naming system for his kids. His son was at the first two initials of DC, his daughter AC. She claims he did it on purpose. All right, so the symbol for an AC power supply is basically a circle with an oscillation back and forth, indicating that we have this basically voltage and current are all both going back and forth. The couple of rules that we're working with here is we do need to worry about instantaneous versus the maximum value. And so the convention is, for example, lowercase is the instantaneous. So in this case, instantaneous current. Capital I is the amplitude of that current. And the same with little v, capital V. And that's, little q and capital Q.
Okay, little I is the instantaneous current, you said?
Yes. So you'll have something like, I have a power supply where although usually use epsilons of not. Something like that. So the instantaneous value of the voltage is found by this formula right here. If we're dealing with our outlets down here, our outlets are roughly 60 hertz. In other words, they're cycling back and forth every 60 seconds. Wow, flip that one. It cycles 60 times every second. So the frequency is 60 hertz. Omega would be the angular frequency, which is 2 pi times f, which is 2 pi times 60, which is, if someone would be kind enough.
125.
Yeah, I was hoping for something more specific than that. Read something. Somewhere around 370, I think, but.
376.99.
Units? So when you're doing it using an AC power supply and you do a curve fit, you'll get a bunch of data points like this. You'll get a curve fit. You would expect some number somewhere around there to be the coefficient of time.
You said that was just for like a power?
Yeah, for the United States. Now Europe is mostly on DC, mostly all. I think they're all on DC. I know you've lived in Europe for a little bit. Did you ever face any AC current?
Not sure. I really don't know.
Oh. That wasn't the first question you asked when you came? All right.
Doesn't it run at like
I
half
know
that
it's like
frequency?
240 volts, but I don't know where that, or was it volts or what? Something with 240, but I don't think that's that relates to anything.
Somewhere I've got the table of what Europe does. But it might take me a while to find it, so I'm not going to look for it. Oh, there we go, found it. Let's see. Europe is 240 volts, 50 hertz, according to this chart.
Yeah, I knew the hertz was lower.
Is there a reason why the plugs in Europe are different from the ones here? Or is that just?
I don't know whether it's a matter of to prevent people coming over there from, oh, let me just plug our device into the outlet, or whether it was just different standards were set at different, independently of each other.
Probably.
I don't think there's any physical reason or physics reason why that has to be that way.
It's probably different standards, because if it was just to prevent people from like plugging stuff up whenever they come over, then they wouldn't make adapters.
Yep.
Unless they just wanted to make adapters to make more money.
It was established by Big Adapter,
Yeah.
or constantly controlling the current market. Now, the reason why we're on AC versus DC is that frankly, because the US is so much bigger than any of the European countries. I'm not counting Russia as a European country. So, because we have to transport current over a much larger period, or a much larger range, there's much less power loss when you're doing AC than with DC. Now, that's when it first started. Edison was a huge advocate of DC. Westinghouse stealing Tesla's technologies, or with Tesla's work, and wanted to make AC work. Edison wanted to give AC current a bad name, and so electrocutions were done with AC power because they wanted people to associate AC power with death. And they even electrocuted an elephant using AC. Back when you could just do about anything. And however, there was a huge contract fight that Westinghouse won to get power out of Niagara Falls, and that basically cemented it. That was probably the biggest defeat for Edison. He had to die rich instead of filthy rich. All right, so if I have the simple R circuit, I've labeled this with the magnitude right here. I probably should be more specific, and this is that epsilon naught cosine omega t. I could throw a phase shift into it, and experimentally you will, because odds of starting your graph perfectly when time is equal to 0, in other words, you're at your maximum when time is equal to 0, slim to none when you're actually doing it experimentally. So technically there's a plus phi out there when you do that lab in 2 weeks, I guess, or a week from Thursday. I know that the voltage gain across the power supply plus the voltage gain across the resistor is equal to 0. And so this becomes, actually, I actually do want to make that negative. So I said epsilon sub naught cosine omega t minus IR is equal to 0. And then notice it is a lowercase I there. And if we solve for I is equal to epsilon sub naught over R times the cosine of omega t. This is not particularly earth-shattering, but if we're going to go through a similar process with the capacitor and the inductor, and we will get something different in those cases. I wonder if my car's warranty is expired.
Probably is.
So if I look at the current of the power supply, it looks something like that. if I do the current of the resistor, and well, it's the exact same. The reason why I drew this graph here with one on top of the other one is I want to emphasize the fact that when you're dealing with resistors, and this is a rather critical rule here, voltage and current are in phase. Actually, I should have drawn the voltage across the power supply or the resistor. There we go, that would have been better if I'd done that one. They're in phase. The amplitudes are not the same, they're on different scales. But it's not uncommon to draw them on one graph like that, and you will too when you do the AC lab. Obviously, my emphasizing this should be a slight hint, a little teaser to the idea that when we deal with capacitors and inductors, it will not be in phase.
What about VR? That wouldn't be in phase.
This is the voltage of the power supply and the resistor.
Oh,
They're together. It's all in phase. The voltages, when you plot them, should look identical. And then the currents should look identical. But the current and the voltages should be off by some amplitude. If I drew this in a slightly different format, and this is the format generally when you're solving them. Now, there is a way of solving them without using what are called phasor diagrams. I've had students in here who have had different ways of doing it. It brings in complex numbers. I do not do it that way. I do it with phasors, which is typically the way it is done at this level of physics. If you have a different way of solving AC circuits, bringing in complex numbers, go for it, if you know how to use it. You can think of a phasor very much, it's kind of like a vector, except a phasor is more like a spinning vector. The amplitude, or the size of phasor, represents magnitude, or I should say amplitude, of a quantity. The projection onto the horizontal axis is the instantaneous value. So my hypotenuse represents the magnitude here. So if we're dealing with, if this were the voltage phasor for the power supply, this would be epsilon sub naught, and the instantaneous value would be this lowercase v. This angle right here is theta, which is omega t. And so looking at my right triangle there, I have an angle omega t, hypotenuse of epsilon sub naught, and the horizontal value of v. And so the cosine of omega t is v over epsilon sub naught. And if I multiply both sides by epsilon sub naught, I get my formula here. So if I did a phasor diagram of my R circuit, it is going to look so incredibly exciting here. I have a phasor here, which I would label as epsilon sub naught, and then VR. They are generally labeled by the magnitude of them, in other words, the amplitude. And then my current. Now, whether my current phasor should be larger or smaller depends upon the numbers I actually give you. If you're not given numbers and you're just given letters, pick one. I generally make the second one smaller than the first one I draw. And this will be I power supply and I for the resistor. These phasors are spinning around the center at an angular speed of omega. And so that's the basic introduction to phasors. It really doesn't tell us a whole lot that we didn't know already, but it is something that will be an incredibly useful tool as we get into more complex systems. All right, questions here before we do the C circuit. Yeah, you heard that right, the C circuit. So voltage from the power supply minus the voltage from the capacitor is 0. Sweet epsilon sub naught cosine omega t minus voltage from my capacitor. Well, the same basic rule applies that my capacitance is Q over delta V. Sort of think of that as the model. So delta V is Q over C. So this is going to be lowercase q over my capacitance equals 0. Solving for Q. Q is going to be, so you bring that over, multiply times C, so it's epsilon sub naught times C times the cosine of omega t. Now let me make sure I didn't get a minus sign in the wrong spot. Because that would really screw things up. So far, so good. What I want to know is the actual current, though, because when I'm doing my comparisons here, I'm looking at voltage and current, not charge, and so I need to figure out what is the current flowing. And again, we run into the situation of the charge on the capacitor is a derivative of the current, or sorry, the derivative of the charge is equal to the current, but we do need to worry about a negative sign. And so I know that the current flowing onto the capacitor is equal to dq dt, and there is a negative there. And so I sub c is equal to the negative time derivative of epsilon sub naught c cosine of omega t, which is epsilon sub naught c omega sine omega t. I did cancel them here. However, I'm questioning that. All right, so Q is the charge that is on the capacitor itself. If my current is flowing, so if I think about this as a positive sign and a negative sign, as current is flowing onto it, dQ is increasing. So if I consider that to be the positive direction, that actually should be a positive there, and that should be a negative. So if I plot my voltage versus time, the voltage for the capacitor and the AC, the power supply are going to be the same, they'll be in phase. So that's my voltage curve. My current, though, is a negative sign, so sign looks like that, so negative sign is going to be like that. So this is my current here in black. So if we think about it, if I'm going from left to right here, if I think about the peak here and the peak here, well, my current comes first. So for capacitors, there we go. I leads V, because I sub C equals V sub C by, well, it's out of phase by 90 degrees by pi over 2. That's V sub R.
Would it also have a high amplitude?
The amplitude would be, that's the amplitude of the current. You said higher amplitude?
Yeah, would the current amplitude be higher than the voltage amplitude?
They're dealing with different units, but in terms of the actual number, not necessarily. It depends on the values of these other things. Capacitances are usually millifarads or smaller, often microfarads. Omega is 300, and whatever that was.
And it would be the same for both. Omega would.
Presumably, if you're using the same power supply. If I drew my phasors for my C circuit, I have epsilon sub naught and V sub C. The voltages are in phase. However, the current for the capacitor leads by pi over 2. And so my capacitor phasor, whether bigger or smaller, it's a 90-degree angle. This would be my pi sub C. And it would also be high power supply. You might have guessed that inductors are going to lag by pi over 2. But fortunately, a student gave me a memory trick a couple years ago, which we will exploit. Any questions before I erase what I just did? So let's deal with the L circuit, and then we'll actually start putting stuff together. L circuit. AC power supply, inductor. The voltage here is characterized by epsilon sub naught cosine of omega t. V sub power supply minus V sub L is equal to 0. And so we get epsilon sub naught cosine omega t minus L the I dt, lowercase I dt is equal to 0. So epsilon sub naught cosine omega t is equal to L the I dt divided by L. So epsilon sub naught over L cosine omega t is equal to the I dt. And this is the current flowing through the inductor. And that's epsilon sub naught over L omega sine omega t. So if I collide them, I have voltage. And then my current flowing through the inductor is a sine curve. So as we move from left to right, yeah, no, okay. V peaks before I does. And so for inductors, I sub L lags V sub L by pi over 2. So if I did my phasor diagram, I always draw the first one in the first quadrant. You don't have to do that, that's just the habit I'm in. Epsilon sub naught, V sub L. Again, this thing is spinning around counterclockwise, and so lagging means it's behind it by 90 degrees. And so this would be I sub L. So we have 3 crucial rules right there when dealing with more complex circuits. And the way that, when I got to this point, I always, whenever I'm doing the derivation in class, I get to the point where, as you saw, I take that pause and I'm going, wait a second, did I get that backwards? And then what I went back to was what that student had told me. Eli, Iceman. If you look at older textbooks, they often, for voltage, they'll use a capital E, which is unfortunate. E comes from the fact that they originally dealt with EMF. Epsilon is typically what is used today, but in older books, it was a lot harder to put in other type prints other than just the classic Western Europe prints. And so E often is used for voltage. And so for an inductor, voltage comes before the current. For a capacitor, current comes before the voltage. All right, a couple more rules we need to deal with. Two more letters for our vocabulary. X represents reactance. And Z is impedance. It is not impedance, it's impedance. When we're dealing with an individual thing, so for example, there's going to be capacitive reactance and inductive reactance. Basically, it's sort of a force fit into Ohm's law. V equals Ix, so this would be Vc is equal to Ix sub c. That's an I there, and VL, shockingly, is going to be Ix sub L. And I should try and make the L's look less like C's. Impedance is for the entire circuit. And so epsilon sub naught, in other words, the amplitude of the power supply, is equal to I times